Hello and welcome to section 6.2. We're talking about energy changes. So we need to know how we can measure energy changes, and that's what we're going to look at today. We're going to look at the idea of calories, joules, and specific heat capacity. First, let's look at the calorie, and a lot of you probably think, at least the first thing that comes to mind might be, you're not supposed to eat too many of them, right? Well, calories are measuring energy, right? 5 pounds of spaghetti, for example, there's enough calories in 5 pounds of spaghetti to brew a pot of coffee. Or in a piece of cherry cake, we have enough energy in the form of calories to light a 60-watt light bulb for 1.5 hours. Or 217 Big Macs might drive your car for 88 miles. So think of calories in terms of energy. The definition of a calorie is exactly the amount of energy needed to raise 1 gram of water 1 degree Celsius. That is the definition of a calorie. If we wanted to raise a kilogram of water, it would take 1,000 calories for each degree. There's the math behind that. One thing to note, when people talk about food calories, those are spelled, that kind of calorie is spelled with a capital C to differentiate it from the kind of calorie we talk about in science. And it is actually a kilocalorie. So that's just the difference. When you're looking at your food calories, those are really kilocalories, not actual calories. What's a joule? You've heard of joules. They're another unit of measurement, of measuring energy. And 1 calorie, the definition of 1 calorie would be 4.184 joules. We often write them this way, abbreviate calories just lowercase cal, and joules can be abbreviated by a capital J. So let's try a little conversion, and you should know how to do this from all of our calculating before. We are going to convert between calories and joules. If I have 60.1 calories of energy, how do I write that in units of joules? So we have our 60.1 calories. We know that from here, from our problem. And we're going to do dimensional analysis, right? We're going to multiply by our conversion factor. Our conversion factor is this: 1 calorie equals 4.184 joules. So let's write that down. Which one will go on bottom? The calories we want on bottom, so that these two will cancel out. So 1 calorie equals 4.184 joules. And when we multiply that out, 60.1 times 4.184 equals 251. We're left with joules for the units. Calories cancel out, and there you have it. So you try it. How many calories of energy correspond to 28.4 joules? This time you're going from joules to calories. So see if you can do that on your own. So your answer should be 6.79 calories. There'll be some more practice at the end. So let's look right now at calculating energy requirements. And I'm going to show you 2 different ways to do this. The first way really is the more difficult way. I'm going to explain how we come up with really the formula that eventually I'm going to show you. So I'd first like to work through it logically with you. So here's an example. What if I have, I want to find out the amount of energy in heat and measure it in joules that is needed to raise the temperature of this much water. I know the grams of my water, and I want to raise it this much, 29 degrees to 46 degrees C. How do I go about tackling a problem like this? So I'm going to draw a little diagram here. I know I'm starting with 7.40 grams of water. The temperature of that water is 29.0 degrees C. And I want to know how much energy does it take to take that same water, 7.0 grams of water, and raise it to a temperature of 46.0 degrees C. Well, I know this. I know that 1.00 grams of water, if I were to raise it 1 degree, so let's say I'm going to start out with only 1 gram of water and my temperature is going to be the same, 29.0 degrees C, but I'm going to raise that 1 gram of water to 30 degrees C. I know that that is 1 calorie. Remember that? And 1 calorie equals 4.184 joules of energy. So I know that's how much energy in joules it would take to raise 1 gram of water 1 degree. So what if I were to, instead of 1 gram, let me raise 7.40 grams of water 1 degree Celsius. So I'll start out with my temperature of this, and I'm going to end up with 7.40 grams of water at temperature 30 degrees C. Well, I'm going to still, if it were only 1 gram, it would be 4.184 joules. But instead of simply, switch colors so it makes it easy to see, instead of just 1 gram, it's 7.040 grams. So I'm going to need to multiply this by 7.40 grams. That is going to be how much energy I need to raise 7.40 grams of water by 1 degree Celsius. Now the problem is, I don't want to raise it just 1 degree Celsius. I want to raise it, well, the difference between those temperatures, delta T, is 17 degrees Celsius. If I take the difference between these temperatures, right? If I take 46 minus 29, I get 17.0 degrees Celsius. If I'm raising the temperature by 17.0 degrees Celsius, I need, let's add another color here so that we don't get so confusing. I need to multiply this by 17 degrees Celsius because I'm going that many, I'm raising it by that many different degrees. So our answer in joules is going to be 4.184 joules times 7.40 grams times 17.0 degrees Celsius. And when I multiply those together, I get 526 joules. Now let's see if you can try a problem like this. Here's one to try on your own right here. How many joules of energy are required to heat 454 grams of water from 5.4 degrees Celsius to 9.6 degrees Celsius? Pause the video and try that problem, and then you can continue. Now, let's just review. We've talked about what is required, basically, to change the temperature of a substance. We've been talking about water. We know that mass is involved, right? If I raise the mass, I have more mass of water, it's going to require more energy, right? That's why we multiplied by 7.40 in that last problem, because there was more mass. The number of degrees that I am changing that also will require more energy. The amount of energy required as heat to change the temperature definitely depends on the number of degrees I'm changing it. The third thing that is really crucial in how much heat is required is the identity of the substance itself. So far we've been talking about water, but what if we talk about something else? I don't know if you've noticed this, but different materials heat up at different rates. Let's look at just the difference between gold or aluminum. Gold heats up about 7 times faster than aluminum. And you know this because, when you're cooking or when you're doing different things, different substances definitely heat up at different rates. A wooden spoon definitely does not heat up as fast as a pot or a pan, right? That has to do with its conductivity. But the identity of the substance itself will vary greatly. We call this phenomenon a substance's specific heat capacity. Sometimes it's shortened to simply specific heat. Those mean the same thing. And the idea of that is that different materials store different amounts of heat energy. Water happens to have a really high specific heat capacity. It takes about 30 times longer to heat than gold. Therefore, it cools down much slower as well. It stores about 30 times more calories than gold when we just compare it to gold. It has a really high specific heat capacity. The specific heat capacity of water is defined as 1, and we write it in these units. 1 calorie per gram degree Celsius. The gram and the degree Celsius are on the bottom. 1 calorie for every gram and for every 1 degree Celsius. And you know that because you know it takes 1 calorie to raise 1 gram of water 1 degree Celsius. And that is our definition of specific heat for liquid water. If we convert that to joules, come up with this nice little chart here. In joules per gram degree Celsius, liquid water is 4.18 joules per gram degree Celsius. For ice, it would be a little bit different. Water vapor, dry air. Here are some other materials. Iron, here's its specific heat, 0.45 joules per gram. Copper and lead. So now let's try a little problem here. What quantity of energy in joules would be required to heat a piece of iron weighing 1.3 grams? And we're going to raise it from 25 degrees Celsius to 46 degrees Celsius. And I'm telling you that the specific heat capacity of iron is this much, 0.45 joules per gram degree Celsius. And we'll do the same thing we did for water in our other example, only instead of 4.18 joules to raise 1 gram of the substance by 1 degree Celsius, it's going to take 0.45 joules to raise 1 gram of the iron 1 degree Celsius. So here, I just wrote it out like we did before. How much energy is going to be required to take 1.3 grams of iron at 25 degrees Celsius and take that exact same 1.3 grams of iron to temperature at 46 degrees Celsius? So we can step back and look at just 1 gram of iron, okay? Because the heat capacity of iron is 0.45 joules per gram degree Celsius. So we know that it takes 0.45 joules of energy to take 1 gram of iron and raise it just 1 degree. So this is true. We know that raising 1 gram of iron 1 degree will require 0.45 joules of energy. Now what if we want to just raise the 1 degree, but we're going to talk about 1.3 grams of iron? We're going to have to multiply that 0.45 joules of energy by 1.3 grams. And that will give us the amount of energy needed to raise 1.3 grams of iron by 1 degree Celsius. Now again, if I want to raise it more than just 1 degree, I'm going to need to multiply by that change in temperature. I'm raising it not just 1 degree, but I'm raising it 21 degrees. 25 degrees to 46 degrees is times 21 degrees C. So if I take 0.45 joules times 1.3 grams times 21 degrees C, that will give me my answer. Joules. So one thing here, I wasn't completely clear. This would be joules per gram degrees C. We have the grams canceling out. We have our degrees C canceling out, and we're left with only joules, and that's how those units work. So you give it a try. Here's a practice problem for you to try. Pause the video and see if you get the answer right. Okay, that brings us to an important formula. And this is going to make your calculations even easier because you can simply plug and chug, right? Plug values in and chug away on your calculator. So here is the formula. Q equals SM delta T. Let's go over what all these mean. Q is the energy or heat that is required. We're using a capital Q this time instead of a lowercase q. By the way, here was your answer to the problem before if you didn't see it, 8.1 joules. S in our equation stands for specific heat capacity. M is the mass of the sample in grams, and delta T is the change in temperature in, should say Celsius, not Celsium, degrees. This is in essence what we've been doing. You could have come up with this formula all on your own, even if I hadn't given it to you, but I'm going to give it to you. That makes it really easy. Let's do an example together. We have 1.6 grams of a metal, and this metal looks like gold, but we don't know if it is. It requires 5.8 joules of energy to change its temperature from 23 degrees C to 41 degrees C. Is the metal pure gold? And by the way, the specific heat capacity of gold is 0.13 joules per gram degree Celsius. So we should be able to figure out if this metal has this specific heat capacity or not. That will tell us, is it gold or is it not? So let's start with what we know. I know 1.6 grams is the mass. I do not know the specific heat capacity. That's what I'm looking for. So I'm going to put an S for the specific heat capacity times my 1.6 grams for the mass. I know that my delta T, my change in temperature, is going to be 41 minus 23. I'm raising the temperature from 23 to 41, so that's going to give me 18 degrees C for my change in temperature. Now I can put Q in. Remember, Q is the energy or the heat required. That's 5.8 joules. So I'll plug that into the equation. So here I have for Q 5.8 joules. For S, I don't know S. That's what I want to find out, the specific heat capacity. My mass is 1.6 grams. My change in temperature is 18 degrees Celsius. And now I can simply do the math. If I multiply 1.6 times 18, I get 28.8 gram degrees C. I just rewrote the rest of the equation. Now I can divide both sides. If I divide this side by 28.8 gram degrees C, and I divide this side by 28.8 gram degrees C, I end up with my specific heat capacity. These two cancel out, and I get S equals, I change that color for us, S equals 2.20 joules per gram degrees C. That is my specific heat capacity. Is that the same as the heat capacity of gold? No, it's not. So this must not be pure gold. Here are some problems for you to practice. You can read them right here off of the video. I also have copies of these in class if you prefer them that way. The answers are on the next frame as well. You will, for some of your problems, you'll need to use this little specific heat capacities table to get some specific heat capacity values, and have fun doing these problems. I'll see you in class. Here are the answers to those problems that you did, and I'm sure you got them all right, and you're doing great, and this is exciting. It's not too hard. Here are some advanced ideas. If you come up with other ideas, please look into them. I'd love to see what you come up with, and I'll see you in class.